Hello everyone and welcome to your computational practicals introduction. So, basic introduction to computational chemistry. This slideshow or little presentation I put together is more like an information session than something that you really will be able to understand. I don't expect you to understand everything because I do know computational chemistry initially it's not really the same as anything you've done before. And even the quantum chemistry that you have done or will do is not going to really aid your understanding computational chemistry directly, because computational chemistry, of course, has its own. It's basically a field on its own. It's different from quantum chemistry, but they go hand in hand. So sit back, relax, listen to my voice, and I hope you enjoy it. So let's start with a basic idea. So computational chemistry, of course, uses computers. Big shock, I know. To solve chemical problems. And when we say problems, we mean all sorts of chemical equations, help us give energies for systems, reactivity, reaction mechanisms, that kind of thing. So any chemical calculation you've ever done, not necessarily like calculation as in, for example, the number of moles. That's not what computational chemistry is. How many moles reacts with how many moles? That's not what it is. It's more in terms of energetics, and basically energy forms the basis of all science. So if you have an equation for energy, you can use something called Hamiltonian mechanics, which you should be familiar with because you have the Hamiltonian in the Schrödinger equation. You also have Hamiltonian mechanics in classical mechanics. And from that, you can basically derive anything you want: position, momentum, time dependence, whatever. So the energy forms the basis of anything. Anyway, so we use a computer to get the energy, and then we get a whole lot of other stuff as well. And these calculations are, of course, based on theoretical equations. And sometimes, or not sometimes, we always have to compare. We're still in the stage where we need to compare with experimental results. So we're not quite at the stage where people have taken that computational chemistry is indeed correct and completely covers all aspects of chemistry. So we still need to compare to experimental results and see if it is, or it complies or predicts the same as the experiment does, or what our intuition says. Even though it's starting to get to a stage now where people believe that there are certain things that experiments can't explain, or what we don't see in experiment, which can be seen on computation. And that gives a whole lot of debate. And then people shout at one another, and that's all fun. So, okay, typical results, just to cover a few things that you can get. We can get the molecular structure, and like we say, relative of the energy of a particular structure, or at least relative energies. So meaning we can't necessarily get this specific energy, but we can say this one is more stable than that one. Two structures, if you compare them, this one is more stable than the other structure, or something like that. You can also predict all sorts of optical, electrical, magnetic properties. Optical properties, sometimes, remember, optical means or electromagnetic radiations interference with matter. So in other words, how will something react to matter or electromagnetic stimulation? Not optical. So it's optical in the sense of like your glasses, optical, but in terms of chemistry, it's more electromagnetic radiation stimulation. Electricity, I'm sure you know that, and magnetic properties. You can also do geometry optimizations. So remember in your first year inorganic chemistry, you looked at, this is the conformational analysis of butane. And you had those gauche and anti-periplanar and etc. kind of arrangements that you looked through Newman diagrams with. And for example, computational chemistry can help calculate this graph that you see here. So in other words, which tells us this is the lowest energy conformation, and that is when the two methyl groups at the ends of butane is opposite to one another, which is of course intuitive, but now we can see it's definitely zero at that, and whereas it has different energies at different other configurations, and in between the configurations we can also determine the energy. We can also compute spectra. For example, this is an IR computed IR spectrum, which, and so you can compute IR, UV, you can compute NMR, anything you really want from computation. And we can also determine reaction mechanisms. So if you are unsure of how a reaction proceeds, you only, because it's experimentally, you're going to add a few things and then you're going to see what the product is. And then you might be unsure as to how exactly does this occur. For example, this mechanism is quite complex. So how would you know there would be a carbocation rearrangement from a secondary carbocation to a tertiary carbocation? You would only know that if you actually looked at it computationally. And most of the mechanisms you see in your organic textbooks are actually determined using this method. You can do it experimentally, but that takes a lot of time, whereas computationally it's much easier to do it. Okay. In computational chemistry, we get two main types of methods. The first being molecular mechanics, which is what we'll be using in this practical. And the second type is electronic structure methods, which is the more rigorous way of more rigorous computational method, and involves a lot more theory to do. But let's first speak about the molecular mechanics. The molecular mechanics uses classical mechanics to model the system, and essentially you look at atoms as balls of charge. So as you would have two macroscopic balls with a certain amount of charge, positive and negative charge, protons, electrons, and neutrons, you fill them up with a certain amount of charge and you model them as if they had a spring between them and they have some sort of interaction and they move, and you have they oscillate and they move around, and you model them using Coulomb interaction, van der Waals potentials, harmonic approximations, etc. You use the classical mechanics way of writing things, and you apply that to this to the microscopic system. So you use macroscopic ideas on the microscopic system, and we will get into why this is very useful in a second. But because it might seem a bit stupid to say, well, why does this even make sense to apply macroscopic ideas to a microscopic system? It shouldn't be applicable at all. But I promise you will see it is sometimes quite useful, and it can give you some useful results. The other two methods, just for completeness sake, some things that if you continue on with your honors or if you're interested in computational chemistry, which you will get into. The first being semi-empirical. So semi-empirical meaning, so empirical means experimental, right? So it means we make approximations using empirical data. So in other words, you take some data measured in a lab, so something that you know about the system, and you combine that with the theory, so the quantum theory, and you do calculations based upon or based on those things. So you sort of hybridize high level of theory with experimental observations, and you do calculations based upon that. And then the highest level that you get is called ab initio, so meaning from the beginning, or other meaning can also mean I forget sometimes. It's sort of like the fundamental, or from the beginning, from the ground up. Meaning you use only physical constants. So meaning you have electrons, you have protons, you have neutrons. You build wave functions from that, and you calculate all energetics, everything of the system from those points. And you don't think about balls of charge and bonds being vibrational. You just start with the basic makeup of the system, and you build it up from there. You don't make no approximations. You make no use of no data to simplify calculations. You just go from there. Of course, there are mathematical approximations made in this, but there are no experimental or other types of system approximations, if I can put it like that. And then you can get, using this, you can get things like the first Brillouin zone in crystal structures, which is something you will be unaware of, but I drew this picture some time ago, and I wanted to put it in this slide. This is essentially the density of states. So the electrons form around a metal sphere in a crystal structure. This is how the electron wave function looks in a metal, around a metal atom. It's cool, isn't it? So you can get this picture from the mathematics that you derive here. Anyway, but we will focus our attention on this part. So general concepts in molecular mechanics. And molecular mechanics is what we were using in this practical, and I'll explain why. But important for that, so it uses the classical physics laws like Hooke's laws, force constants. If you've done any classical mechanics or any physics, I mean, you would have encountered Hooke's law and some idea of forces. And it doesn't really look at specific, like an electron and a nuclei, or the electrons' interactions, or the electrons' interaction with the nuclei, etc., as the electronic structure methods does. Like I said, it just sees this as like a ball of charge. If you had a big ball in your hand, a sphere in your hand, and you had some charge on it, you would model it as such. Then you can calculate your potential energy, or so in other words, just the energy of your system, because remember, from the energy of a system, you can get any property you would like to calculate using what we call force fields. And the reason for that is, if you think in terms of a potential energy, so the gradient of potential energy gives you the force, so the force is equal to minus the gradient of the potential, or the curl of the force gives you the potential energy. They are sort of linked. If you didn't follow what I just said, just take it that potential energy and fields and force, or force fields, are sort of connected to one another in physics. And the force fields is sort of the approximation to try and include electronic effects, but only to a certain extent. Then, of course, bonds are treated as springs, like we saw on the previous slide. And then you have something called the trading potential. This is just a different kind of potential. Remember, springs are harmonic functions, the harmonic potentials. This just helps to define a better level of theory. So if you look at the molecule, let's say, for example, this is not a real molecule, but this is how molecular mechanics looks at a molecule. So you have balls of charge that are connected. So if they are connected, they can have three kinds of interactions: either stretch, bend, or torsional. And those that are not connected have what we call non-bonding interactions. So if a stretch is a vibration, so in other words, they stretch to either side. A bend, so you can see, you think of a bend as scissors that open and close, and torsional is rotation around a specific bond. And of course, non-bonding, these two are not bonded, and they have some sort of van der Waals interaction with one another. So that's in essence what molecular mechanics tries to do. So it models the system as such using these four fundamental forces. And that is how you come to this equation. So you have the stretch contribution, so all the stretches calculated, so that's what the big sum means: stretch of there, stretch of there, stretch of there, stretch of there, stretch of there. Bond angles, bond angle, bond angle, bond angle, bond angle. Torsion angles, what their relative rotation is to one another, and then non-bonded interactions. For example, this one is also non-bonded to that one, to that one, to that one, to that one. That's why there's a double sum. And double sums tend to be, or to overestimate, but okay, don't worry about that. So you just need to take this equation as, cool, it's just a combination of a bunch of terms. Okay. So to elaborate a bit on these forces, or these potentials that we use in molecular mechanics, so the non-bonded is the van der Waals force, so force van der Waals. Two things that are not bonded, A and B. You have a bond stretching, so meaning bond vibration. So, some stage it was the two dotted circles, now it's moved closer to one another. You also get angle bending, so you have some sort of function dependent on an angle of it, giving you a potential energy. And then, of course, you also get the torsional, which means it rotates in some way relative to one another. Okay. The advantages of molecular mechanics is really fast. And when I say really fast, then I mean really fast. And that is why you can model proteins and massive molecules, say 100,000 atoms molecules, with using this method in a matter of days for the 100,000 and a matter of seconds for for what we're going to do, small molecules. Unfortunately, of course, there are limitations because the way that you're doing. So the moment you have something called relativistic effects, in other words, things like gold has relativistic effects. So that means that there's a mass reduction due to the energy of the atom or the intrinsic energy of the atom. You can't use molecular mechanics anymore. But so that just means we limit it to a bunch of compounds. And actually, when we say compounds, to a bunch of elements, but compounds, elements, sort of the same thing when you look at them in conjunction. And of course, when electronic effects, for example, like spin-orbit coupling, you don't have to really know what that means, but that is when your electron interacts with your nucleus and there's an energy reduction because of that positive interaction, then it also falls apart. But we'll be using it in this practical because then you can do it on your own. You can use a website, which we'll get to in the next video, and then you can do it yourself. So I thought that would be better for you than me trying to do these heavy theory calculations that takes 10 days, and you don't really see any of or you don't get to play around with it. So I think we've made this compromise, but you still get decent information, you still get decent results. And remember, everything is comparative relative to one another. So even though there are errors in this specific domain, molecular mechanics, compared to the other domains or experiment, if something has a lower energy than something else, relatively, the one is more stable than the other. That's a fact. Even though the energy, the absolute energy, is not correct. So meaning, let's say, for example, you calculate the one's energy is minus 50 kilojoules per mole, and the other one is minus 100 kilojoules per mole. The one that's minus 100 kilojoules per mole is definitely more stable, but it might not be minus 100 kilojoules per mole, or its energy is not minus 100. It might be minus 12 and minus 6, but that doesn't matter because relatively we are still able to make certain conclusions. So that is where molecular mechanics actually finds its best application, is in its speed, and because you can still compare things relatively. Though it's not really important for the specific practical, I have included in the practical guide some information regarding electronic structure methods, because I do think it links quite nicely to the theory course, and because the theory course is much more heavier on the ab initio methods, really on the quantum or the hardcore quantum mechanics. And it might be useful for you to have a greater understanding or a better appreciation for what we're actually doing here than just the molecular mechanics. So essentially what the practical guide goes on about is it says, in quantum mechanics, we want to solve the Schrödinger equation, and we want to get this wave function so that we can apply the Hamiltonian and get the energy eigenfunctions from that, right? So we want to get psi, and once we get psi, we apply the Hamiltonian and we get the E functions, right? And from the E functions, we can calculate, we get everything that we want to get, right? So that's essentially what we aim to do. But the problem is to get this psi, or this wave function, is not the easiest thing to do. And then we have the two different kinds of schools of thought. So the semi-empirical and the ab initio methods. And they are essentially two different kinds of mathematical approximations. Well, not mathematical, the one ab initio, you use different kind of mathematical approximations. Semi-empirical methods, of course, uses the empirics or the experimental parameters to simplify the calculations. And they solve an approximate form of this Schrödinger equation. So what they do is they split the Hamiltonian into different parts of it. So they say the Hamiltonian consists of certain parts that they want to calculate, and certain parts of it. So for example, the energy coming from a certain section from the system is already been determined experimentally. So they don't need to calculate that part of the Hamiltonian because they have that value for the energy already. So they can disregard that section of the Hamiltonian. So they chuck it away, and that simplifies the Hamiltonian because you measure that experimentally. Essentially is what it does. So if you can think of the Hamiltonian as the sum of the kinetic and the potential energy, and actually the Hamiltonian is dependent on all the charges and all the interactions of all the electrons and whatever. And if you can say, well, the Hamiltonian is the sum of A, B, C, D, and E, and if we can determine A and C's interactions already, then we don't have to apply A and C to the wave function. We already know what they are, so we can drop them from the equation and we can only focus on the B and the D parts of that equation. Anyway, long story short, sort of fast, lower quality than the ab initio methods. We use experimental values in conjunction with calculations. So it's sort of like when we give you a data sheet and ask you to calculate something from there. Okay, that's what we do here. Then in contrast, the ab initio method uses no experimental parameters. We only use the laws of quantum mechanics and parameters which you can sort of take as fact. For example, the speed of light, Planck's constant. Planck's constant meaning Planck's constant is actually not an experimental fact, but it's a fact of the universe. The Planck length is the smallest length that is possible. That's where Planck's constant comes from. Those kinds of things, the mass of a proton, the mass of an electron, fundamental parameters is what you use. And then you calculate your energetics, your wave functions from there. And an example of that is the Hartree-Fock method. And how these two things link is you need to think of it as, so Schrödinger, Heisenberg, Dirac, all these fancy people, Pauli, they developed quantum mechanics. So quantum mechanics is the theory. That's what you read about in the textbook. Okay, there's not textbooks about quantum or about computational chemistry, but the quantum mechanics, so that's the pure mathematics, the symbols, if you can put it like that. The symbols is the quantum mechanics. Then Hartree-Fock is one of the earliest theories on how would you do this so how would you translate this mathematics into actually calculating stuff for a system and putting it into a computer. Even though in those days when they developed it, the computer was still a fantasy, it was just a logical operating system, a system of, how would you have a logical, systematic operations leading to some sort of calculation. But essentially, so they made that connection. And that is where Hartree-Fock starts. And of course, nowadays you get a bunch of other types. You get like Moder-Plesset. Anyway, getting off topic again. But you can use different kinds of methods that they've developed now how to apply the quantum mechanics to calculate these properties. And that essentially, they all use different mathematical approximations. So Hartree-Fock uses specific things that you can use to input this mathematics into a computer to get the results that you want to get. The drawback of this is this can be very slow to calculate if you want to have high quality. Of course, that's like just as in life. If something takes time, you get higher quality. If you sacrifice a bit of time, then you get a bit of lower quality, but you need to argue what is the point of what you are doing, and then you choose between your molecular mechanics, your semi-empirics, or your ab initio methods. And that's essentially what the differences are between the three of them. So just to elaborate on what the Hartree-Fock method does, so that you understand a bit more, is this is basically trying to figure out how does the orbitals look? What are the orbitals? So remember in 385 you made molecular orbitals from atomic orbitals. And you occupied them, choop, 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 and then okay, and you went on with your life. The problem is the mathematical equations that give you the surfaces of these orbitals cannot be solved analytically. So in other words, you have to do it numerically. And usually when something has to be done numerically, you're going to use some form of iteration. So what you do is you guess. And when I say guess, it's not like an absolute guess. It's a very educated guess. For example, you're looking at carbon. So you have 1s, 2s, 2p, x, 2pz, 2py orbitals to your discretion, which you can use to hybridize, or you can use to build an atomic, to combine to build a wave function. So in other words, we're looking at, I say here except 2p, but you can just ignore that. It's a bit complicated to explain that right now. Just remember that. Just make a note, like a mental note of it. Basically, so you combine all the orbitals in an atom, your atomic orbitals, and this gives you some, and these are known as basis functions in computational chemistry, and it's given the symbol zeta. So the mathematical equation, so 1s orbital is a sphere. What is the mathematical equation for a sphere? Okay, it's 4 pi r cubed, right? So r cubed is technically the square root of x squared plus y plus squared plus z squared. So if you plot that, you're going to get a sphere. Okay, so that's the mathematical equation for the 1s orbital, but it changes, and there's a bunch of things that you will get to in 382 on how to determine different basis functions or atomic orbitals. You know this nomenclature. This is the nomenclature they use in computational chemistry. It's called the basis function because atomic orbitals and the basis is exactly the same thing. So then once you've mixed them, so you've summed together your different atomic orbitals, you get an improved orbital. And then basically what you continue to do is then once you've summed all of them, then you sum them again and you calculate the energy. Then you sum them again and you calculate the energy. And you sum them again and you calculate the energy. So the iterative process, and this is called the Hartree-Fock self-consistent field procedure. So take away from this slide, we mix orbitals, atomic orbitals, they are known as basis functions. So mathematical equations, we sum them together, we calculate the energy, and we calculate the energy again. And the moment that those energy values converge, then we know that it creates a self-consistent field. And that is then the cutoff point. So then we know the equation, the wave function is correct for that specific atom. Okay, so now you start getting why it takes so long, because this is just for one atom. Then you need to do it for all the other ones as well. And sometimes it's not that easy to figure out, to get this iterative process to converge. Okay. So I've neglected to mention one specific method up until now. So we've covered now the semi-empirical methods, we've met the ab initio methods and molecular mechanics. There is another method, and it's called density functional theory, and we'll quickly discuss that just for completeness, so you're aware of it as well. So semi-empirical, we've discussed, we include experimental parameters for our computational. For example, we can use spectroscopic data or ionization energies, etc., to get to calculate what we want to calculate, or simplify our calculations. Our ab initio methods, we use no experimental data. We solve the equations using powerful computational hardware, and we mix the wave functions of our atomic orbitals, so our basis functions, and we get large functions essentially for them to get the wave functions, and then we mix those wave functions and we calculate from that large wave functions for the molecular wide wave functions, and we get energies from there. Then a more modern way, or essentially the way everybody tries to do work nowadays computationally, is sort of a way to use electron density. So electron density as rather than the wave function. So the wave function is your atomic orbitals mixed together, gives you the wave function. And then the electron density distribution over a molecule's atoms can be used to calculate its energies as well. So what do I mean by electron density? Well, so let's look, for example, at benzene here. So we have benzene, and if you remember from geography at school, we could use these maps to identify different peaks. So the red region is high electron density and the blue region is low electron density. And if you use the mathematical surface equation for this electron density distribution instead of the wave function, and you do the calculations based on that, you can also get the energy or the energetic equations that you wish to get. This is a new way that they do it, and it's called density functional theory. So electron density functional theory, because it's a functional theory, so sort of like wave functions, functional theory, it uses density functionals to calculate, because it's actually a function of a function. Anyway, but if you go onto honors, you will definitely cover this in more depth. And if you are interested, you can discuss this with Dr. Lange. He loves speaking about this. Anyway, so that's another method you can do it. But for now, we'll return back to our molecular mechanics. Okay, just to collate all our efforts or ideas. So molecular mechanics, a lot of atoms, quick. Semi-empirical quantum mechanics, quite a number of atoms, still relatively quick, but you know, we need to decrease the number of atoms to get quick results. And if we use ab initio, you can basically only look at 100 atoms. Depending on the level of theory you use, sometimes something might even take up to 2.5 years to calculate. So, and that's just because we're using classical computers. Yeah, and then just a nice little arrow or gradient arrow to explain that here we need empirical parameters, so in other words, experimental data, and then here we solve an approximate form of the Schrodinger equation because certain terms are not left out but are predetermined, and then here we need to solve the exact Schrodinger equation. I say exact, it's not exact with mathematical approximations, of course. Right, so what are you going to do? You're going to complete the assignment. The assignment has a bunch of questions, each with its own idea, and there's going to be little videos that will help you to answer the questions, how to use Beta MolCalc to calculate this. You're going to use the app called MolCalc. You've been introduced to it earlier in the practicals to it. You will use it now a bit more extensively. And of course, the app uses molecular mechanics. So, of course, that's why we've gone through this whole thing, to have a good understanding of why molecular mechanics is what it is and where it fits into the whole computational world. And of course, the reason why we use it, so it gives us good estimations of the actual values in a few seconds. You can use an app or on your phone or tablet, but of course, could give you some difficulty. You probably have figured it out by now, but I would advise you to use a computer, especially now that you're going to use it for more than just IR. And then we will also talk about the different functionalities that you might not be aware of the app in the subsequent videos. Okay, I wish you the best of luck.